This is section 7.3, the section that speaks volumes. The first type of problem we're going to look at is volume using known cross-sections. Here's the example. The region R bounded by the relation x squared plus y squared equals 4, this is a circle, is the base of a solid. So like a pop can. The base of a pop can is a circle. For this solid, each cross-section perpendicular to the x-axis is a square. So it really is, well, it's a little different type of can. Find the volume of this solid. Let's visualize this. So what we're going to do is we're going to lay down the xy axis so that it's the base. And the base is a circle. And the cross sections are squares. So we're going to take a look at what the cross sections would look like. So if we cut this down the edge, down the side, the cross section would be a square, and that'd be, you know, a medium-sized square. On the edge, the squares are going to be a little smaller. And remember that the bases of the squares are perpendicular to the x-axis. So the biggest square is going to be right down the middle. There's the biggest square. And we have to add up all of these squares, an infinite amount of squares. Well, that's calculus, that's integral. So to find the volume, we integrate the area, but a of x dx. And this circle has a radius of 2, so this is going from -2 to 2. And the equation is the square root of 4 minus x squared if we get y to be by itself. The top part is the positive, and the bottom part is the negative square root of 4 minus x squared. So there's the bottom half of the circle and its equation. So we need to find what a of x is. Well, the area of a square is the side squared, but that's not an x. So we have to represent this side with an x in it. Well, if we go from the middle of the side to one part of the circle, that is the square root of 4 minus x squared, but that's only half of the side. Well, if we go from the middle to the other half, that's a negative equation, but remember, we're talking about distance, so we don't really want this to be negative, we want it to be positive. So in this case, the side is represented by twice the square root of 4 minus x squared. And of course that's squared, that's side squared. This whole thing, the inside, represents s. Well, now we just have to integrate from -2 to 2 of, and if I square this, I get 4 times 4 minus x squared. Well, that's it, because the square root and the square cancel each other out. Well, taking the integral is like adding up all of these squares, an infinite amount of them. Well, now we just have to do the math. Let's pull out a 4. And so we have -2 to 2 of 4 minus x squared. I suppose we could distribute it and then take the integral. That'd be just as easy, I suppose. The antiderivative of 4 is 4x, and then we have minus 1/3 x to the third. We're going to evaluate that from -2 to 2. So if we plug 2 in, let's see if we get 4 times, that's 8 minus 8/3, minus, I plug a -2 in there, I get -8, and then plus 8/3. So we have 4 times 8 minus 8 minus -8 is 16, and -8/3 minus 8/3 is -16/3, and this is 48/3. 16 is 48/3, so we have 4 times 32/3, and 4 times 32 is 128. So we have 128/3. Now what do we find? Well, that's the volume of this entire solid. If the base is a circle, cross-section are squares, the volume of that object would be 128/3. Another example, let's look at the same region, but for this solid, each cross-section perpendicular to the x-axis is an equilateral triangle rather than squares. Find the volume of this solid. All right, the base is still a circle. And now the cross-sections aren't squares, the cross-sections are equilateral triangles. And they are perpendicular to the x-axis. So now half of the base goes from the x-axis to the square root of 4 minus x squared. So the entire base is 2 times the square root of 4 minus x squared. You know, this half of the circle is represented by the negative square root of 4 minus x squared, but if we add these two together, we get 0, and certainly the base does not have a length of 0. Well, the area of a triangle is 1/2 base times height. Well, we have the base. This is b right here, so we have that much. Area equals 1/2 times 2 square root of 4 minus x squared. Well, we need everything in x, but right now the height is just h. We need it in x. Let's look at an equilateral triangle. If we call this entire side b, b here and b here, and then if we call this 1/2 b and call that the height, we can find out what h is in b, and then we can write b in terms of x. So h squared equals b squared minus 1/2 b squared. So h squared equals b squared minus 1/4 b squared. And h squared equals 3/4 b squared. 4/4 minus 1/4 gives you 3/4. If we square root both sides, that's going to give us what h is. So square root of 3 over 2b is what the height is. All right, so now we can go back up to our formula. Actually, it's right here. The height is the square root of 3 over 2b, but b is 2 times the square root of 4 minus x squared. So let's see what we're going to have here. The area equals 1/2 2 times the square root of 4 minus x squared times h, which is the square root of 3 over 2b. But this is b right here, so the area equals 1/2 2 times the square root of 4 minus x squared times the square root of 3 over 2. Well, let's make that 2 a little better. Times 2 square root 4 minus x squared. Well, these 2's are going to cancel, and those 2's are going to cancel. And then when I multiply these two together, the square roots are going to cancel. So we need to integrate from -2 to 2, because that's where the circle is. The circle is going from -2 to 2, and we're adding up all of the equilateral triangles that we can make from -2 to 2, an infinite amount. Well, like I said, the square roots cancel, so we're just integrating. I'll pull the square root of 3 out over here. We're integrating 4 minus x squared dx. Well, we've already integrated 4 minus x squared, and it was 30, let's go back, it was 32 over 3, so the answer to this one is 32 square root of 3 over 3. In exercise 1 and 2, this is straight out of the book. Find a formula for the area of the cross sections of the solid that are perpendicular to the x-axis. So we're only asked to find a of x. We're not asked to actually integrate these. The solid lies between planes perpendicular to the x-axis, and x equals 0 and x equals 4. The cross sections perpendicular to the x-axis between these planes run from negative square root of x to the square root of x. So this piece right here is the square root of x, and all of the circles along the x-axis. And this other half is negative square root of x. So the diameter is 2 square root of x, but the radius is square root of x of the circles. And it says the cross sections are circular discs with diameters in the xy plane. So a of x, in this case, they're not squares, they're not triangles, they are circles. And the area of a circle is pi r squared, but the radius of the circle is the square root of x. So a of x equals pi times the square root of x squared. So a of x equals just simply pi x in this case. The cross sections are squares with bases in the xy plane. So a of x equals side squared. Well, half of the base runs from the x-axis to the square root of x, and the other half runs from the x-axis to negative square root of x, but we can't add these two and get 0. That wouldn't make any sense. So, and we're talking about distance, so we're not going to consider this negative. We're going to consider both of them positive. So a of x equals 2 square root of x squared because the base is 2 times the square root of x. So the area in x simplifies to 4x. In letter C, the cross sections are squares with diagonals in the xy plane. So it's not the bases that are in the xy plane, but the actual diagonals. So here's the square root of x, right here, and negative square root of x. And these cross sections in this example are squares with the diagonals running perpendicular to the x-axis. So here's the squares roughly. There's a square. And if we look at this square, first of all, area in x is side squared again. Well, if this is a side, 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 this right here is a diagonal. So if we take the diagonal squared, that equals side squared plus side squared. So the diagonal squared is 2 side squared. Well, if we square root both sides, the diagonal equals side times the square root of 2. But it's not the side that it's not the diagonal we want, it's the side that we want in the formula. So we're going to divide by the square root of 2. So the diagonal over the square root of 2 equals the side. Well, we know what the diagonal is because from the x-axis to the curve is the square root of x, and from the x-axis to the other side is negative square root of x. Well, that's 2 square root of x. That's what the diagonal is. So the side equals 2 square root of x over the square root of 2. Well, now if we plug that side in for the area right there, we get a of x equals, it is 2 square root of x over the square root of 2, and that thing's squared. Well, now we just have to simplify it, and we got it. So a of x equals, that's going to be 4, that'll be x, and square root of 2 squared is 2. So the final answer, the area is 2x. Right there. And we finally have letter D. The cross sections are equilateral triangles with bases in the xy plane. All right, let's draw that one out. There's the square root of x, and the cross sections are equilateral triangles. So the base is 2 square root of x. Well, the height, we already figured that, no use reinventing it. Let's go back to where we figured that out. Here it is. The height is the square root of 3 over 2 times the base. So the height of this triangle equals square root of 3 over 2 times the base. So the area is 1/2 base times height. So we have 1/2 times the base is 2 square root of x, and the height is square root of 3 over 2 times the base, which is 2 square root of x. So these 2's are going to cancel, those 2's are going to cancel. So a of x equals, what's left? Well, we have the square root of 3, and those are going to cancel, those square roots are going to cancel. So x times the square root of 3 is the answer for that one.